Good morning, all. Welcome to the third day of summer school on algorithms. Today we have Professor Arindam Khan. He is an assistant professor at IISc Bangalore. He obtained PhD in algorithms, combinatorics, and optimization from Georgia Institute of Technology, Atlanta, USA. He completed his BTech and MTech from Department of Computer Science and Engineering, Indian Institute of Technology, Kharagpur. In the past years, he has spent some time doing research at TU Munich, ITSIA, Switzerland, Microsoft Research Redmond, UC Berkeley, Microsoft Research Silicon Valley, TU Eindhoven, and IBM Research. Today, he will give a talk on online algorithms. Welcome, Professor Arindam. Over to you, sir.
Thank you for the introduction. And this talk will be on online algorithms. So I'll first start with optimization problems and then define what is online algorithms. And then we'll go over 3 or 4 key online problems. And at the end, if we have time, I'll probably go deep into one of the problems. So let's start with optimization problems. Now, optimization is omnipresent nowadays. And there is a quote by Uber CEO that if you don't optimize for the consumer on the internet, you are dead. So what is optimization? So optimization is the process to find best solution from a set of feasible solutions. And it's ubiquitous in life as we try to minimize cost or maximize profit. So think of examples like where to buy grocery. There are multiple options, which one to choose, or how to score more in exam, which classes to take, how can we get more likes. All these questions are kind of optimization questions. So they are omnipresent in life and we try to minimize cost or maximize profit. So we come across these optimization problems. Now, the problem is these optimization questions may not be easy to solve. They can be difficult. And the difficulty can stem from multiple dimensions. So one is intractability, which is computational hardness, such as MP hardness or P-space hardness or other kind of hardness, because of the restriction on your computational time or space or other resources. So think of examples of problems like, can we color a graph with minimum number of colors? Or can we find an optimal schedule of jobs? Can we find the longest path? So in this kind of questions, we don't know how to quickly find the exact solution of the problem. So the computational intractability is the inherent problem which we come across in this kind of optimization problems. The other kind of difficulty can come from uncertainty. So you may not have the complete data at the beginning. So we have to take a decision without knowing the future. So we only have access to a partial amount of data. Without knowing the future, we have to take a decision. And it's also a very common theme in many practical problems. Should I marry a person or should I buy a stock? This kind of question we don't know because we don't know the future. But we have to take a decision without knowing the future. Now, this two difficulty, intractability and uncertainty, the goal of online algorithm is to solve these two problems and give some approximate solution which can bypass these two kinds of difficulties. So by the way, if you have any question, just stop me at any point of time. It should be a more interactive session. So please feel free to stop me at any point of time. So if you don't have complete input or your problem is difficult, we have online algorithms. So in general, for this kind of optimization problems, there are several algorithmic paradigms, and you may have come across some of them in the summer school. So I will talk about online algorithms, which deal with both uncertainty and the intractability of the problem. Approximation algorithms deal with the case which focuses only on the intractability. So it tries to give polynomial time approximate solution for your problem, optimization problem. And there is parameterized algorithm, where there is some parameter, and based on the parameter, we want to give a polynomial time algorithm. There is dynamic algorithm, which is a variant of online algorithm. So you have some items which appear, some items which leave. So you will come across these two paradigms, I think, in the summer school already. And then there are other paradigms such as distributed algorithms, parallel algorithms, randomized algorithms. Streaming algorithms is also will be there in one of the lectures this summer school, and quantum algorithms. So there are multiple paradigms of algorithms just to know that you can handle these difficulties of optimization problems through multiple routes. But in this talk, we'll only focus on online algorithms. So let's see what is online algorithms. So our goal is to efficiently optimize a problem under uncertainty. So in general, if you have an offline algorithm, then we have access to the complete input in the beginning. But in case of online algorithms, we don't have access to complete input at the beginning. And this is a very well-studied area in theoretical computer science. There are multiple textbooks. And I'll also mention a lot of resources about this area at the end of the talk. But these two are the key textbooks in the area. One is by Alan Borodin and Ran El Yaniv on online computation and competitive analysis. Other one is a survey on online algorithms by Fiat and Ujinger. So let's see what is online algorithm. So there is some underlying complete input. You don't know what is the input, and you don't have access to the full input at the beginning. And part of this input arrives sequentially over time, and we call this arrival order. And decisions for each part must be taken without the knowledge of the future input. And whatever decision you take, it is immediate, you have to take very quickly, and it's irrevocable. So once you take a decision, you cannot change. And the performance quality we measure for online algorithms is by competitive ratio, which is, I will define it again formally, which is intuitively the worst case ratio of the cost of the decision maker and the cost of the optimal offline algorithm. So think of one example. So have you played this game called Tetris? Any of you? You can say yes if you have played. Maybe it's not that popular. Okay, there is some people who have played it. Yeah, so in Tetris, you can think of it's actually online optimization question. So what happens in Tetris is you have some geometric objects, so like this kind of blocks of rectangular blocks or some kind of polygonal axis parallel polygonal blocks. There is some underlying input, but you don't know what are the blocks that will come, and these blocks appear one by one. So in this step, for example, this block has appeared, and without knowing the future input, you have to place this block in this region. And if you, for example, place this block here, then what happens is if you fill up one particular row completely, that row vanishes. So your goal is to fill up these rows such that a row becomes completely full, then it vanishes and it goes down. And at the end, if you're not able to, the game stops when you cannot really vanish the rows anymore and they touch the top boundary. So it is exactly an online algorithm question that you have underlying input, you don't have full access. The part of the input arrives sequentially over time. And once this thing comes, you have to take a decision immediately and irrevocably. So you have to place it maybe here or here, wherever you want to place. But it's very quick. You cannot wait for 1 hour because this object stays for maybe 5 seconds or something. And once you place it, you cannot change it. It is there. So it is irrevocable. Okay, is the setting kind of clear? Yeah, if you have any question, please stop me because this is the beginning, the setting of the problem. And I mean, we'll come across many problems and we'll see how this works. But remember this thing that we don't have access to full input. The input arrives sequentially over time. So there is an arrival order by which the input parts of the input arrives. And the decisions we take in this particular case is immediate. So it should not take too much time. Let's take a polynomial amount of time in terms of input, and it should be irrevocable. And so let's take one example of such a problem. So think of the taxi dispatching of Ola or Uber, which is related to a problem called K-server or K-taxi. So there are K-taxis. And then some people arrive and you have to assign a taxi to a rider. So maybe ride requests are coming online one by one, and you don't know where the ride request will come from. So maybe first one, Chaturvedi comes and he asks for a taxi, and you want to assign these taxis to the riders such that you minimize the total travel distance of taxis to serve a series of pickup requests. Because this travel is kind of waste. You're not getting money for this travel. So you want to minimize the total travel distance to serve a series of pickup requests. So in this case, maybe you assign the closest taxi to him. So this taxi gets assigned to him. And maybe then Dexter comes. And then probably you assign the next closest taxi, this one. Now, note that the input arrival order plays a role in the competitive ratio here. So or the performance of the algorithm. So in this particular case, if Yatayodhuri appears and then Dexter appears, in this algorithm, we pay this cost plus this cost. Whereas if the order was different, first Dexter arrived and then Yatayodhuri, then we could have assigned like this, which is much cheaper compared to the blue one. So blue one, as you see, it's a long distance, whereas the black one is kind of short. And actually it is the optimal assignment in this particular case. So there are 2 points. One is the optimal solution depends on arrival order, and also optimal solution does not depend on the arrival order, but the performance of the algorithm depends on the input arrival order. So is the problem fine? If you have any question, please. There are a lot of comments in chat, I guess. Okay, all are saying yes. Okay, so now we kind of got the motivation of the problem. So why we should study online algorithms? So one thing is most practical problems are online in nature, and we need fast solution for them. So in a way, our life is an online optimization problem. We don't know the future and we have to take a decision quickly. So online algorithms kind of formalizes that kind of problems. And it actually provides a mathematical rigor to study and analyze heuristics. So you can propose many solutions, but which one is good, which one is bad? To justify that, you need some kind of analysis or some mathematical rigor. And the techniques from online algorithms help you to study this kind of problems and give a nice analysis. Another point is it has nice interplays with different areas. There is areas like approximation algorithms, online learning, convex optimization, information theory, communication complexity. So all these areas have nice interplays with this online algorithm. We'll see later that how the techniques from one area helps in other areas and what's the connection. This also gives a metric for difficulty of different discrete optimization problem. As I mentioned, there are maybe 2 problems and both are NP hard, but maybe they're different in difficulty. So maybe one is very difficult to solve in online case, other one is maybe you can get a constant approximation or constant competitive algorithm in polynomial type. So to define the difficulty metric, one can study online algorithms to find which one is harder and which one is not. Another thing is cool. The mathematics behind online algorithms and the problems are really cool in nature. So it's fun just to study these problems from the mathematical aesthetics point of view. So now we are motivated. I'll go to competitive ratio. How do we measure the performance of online algorithms? So a minimization problem. So think of the previous case of this taxi assignment. So there we wanted to minimize the distance. So in some problems, in optimization problems, we try to minimize some objective. And in some problems, we want to maximize the objective. In a minimization problem, an algorithm is called alpha competitive, where alpha is a factor more than 1, if this condition happens. If opt_i is less than equal to ai is less than equal to alpha opt_i plus c. So opt_i, and it is for all input instances I. So think of one input instance I. Opt_i is the optimal solution of the problem on this input instance. So as it's a minimization problem, your algorithm will return something which is greater than equal to opt_i. So this part is trivial from the definition of optimality, that opt_i is less than equal to the solution provided by your algorithm on input I, that is ai. Now what we want to show is this solution provided by your algorithm is not too bad. So it is okay, it is greater than equal to opt_i, but it is not very far from opt_i. Let's say it's 2 times opt_i or something like that. So there the upper bound comes. So it is less than equal to alpha times opt_i plus c. So think of a case like ai is less than equal to 2 opt_i plus maybe 3. So here alpha equal to 2. So that means if opti is equal to, let's say, 1000, then you get a solution within, which is 2003, less than equal to 2003, which is not too bad, within a factor 2, roughly within a factor 2. Now here I wrote C to be a constant. The reason I wrote C to be a constant is normally we are interested in the asymptotic case when opt is very large. So you can kind of ignore C at that point of time. Think of opt is 10 to the power 6 or something. Then 3 is very small. So you can kind of ignore. And then alpha, or factor 2 in this case, is the competitive ratio that you're interested in. So the reason this C is ignored is there could be some problems where the pathological bad examples comes when opt is very small. So for this example, if opt is equal to 1, then this 2 times opt plus 3 is just 2 times 1 plus 3, which is 5, which is kind of bad. I mean, it is showing that the ratio of the opt and AI is 5, but it is only for a small value of opt. In the asymptotic case, it becomes 2. Asymptotic means opti is tending to infinity or very large. So then compared to opti, the term which is additive, this 3 is very small and you can ignore it. That's the reason we have this C as an additive constant, and we mostly focus on alpha, which is the competitive ratio when opt is large. But you can still focus on the case where you don't have C, but you only have this AI is less than equal to alpha opti, and then we call the algorithm to be strictly competitive. So in the previous case, this 2000, this 2i plus 3, the algorithm is 2 competitive, but the algorithm is 5 strictly competitive. Because when opt is smallest, yeah, can alpha be a function of n? Yes, alpha can be a function of n. But I mean, we normally try to find something like constant, but in some problems we'll see you cannot get better than, you will not be able to get constant. So we'll have log n or some other kind of function of n. Yeah. And similarly, you define for maximization problem, the competitive ratio to be AI is less than equal to opti is less than equal to alpha AI plus C. So it's a maximization problem. So then instead of opti less than AI, like minimization problem, it's opposite. So now your algorithmic solution AI is at most opti, because opti is a maximization, it's a maximization problem and optimal solution is the best. But then what we want to show is your solution is not too bad. So it's the opti is at most alpha times AI plus C. And we normally look for polynomial time algorithm. So technically, there is the difficulty of online algorithm, as I mentioned, it can stem from 2 things. One is intractability, other one is more information theoretic problem that we don't have access to the whole data. So for some problem, even if you give exponential amount of time or unlimited amount of time, you cannot really do better. For some problems, you cannot get optimal solution because of you don't know the full data. But normally our goal is to get a polynomial time algorithm. So we'll try to find a quick algorithm, efficient algorithm in polynomial time, which will be solving both the problem of intractability and uncertainty. But as I mentioned, in some cases, maybe you really want to solve only uncertainty and you don't care about running time. There you can go for unlimited amount of running time or exponential amount of runtime. But in this talk, we'll only focus on polynomial time algorithms with good competitive ratio. So let me know if you have any question on the competitive ratio, because it will be crucial in the analysis. So I'll pause for maybe 10 seconds. If you have any question, let me know. So now let me define the types of adversaries. So in a way, you can think of online algorithm as a game. So the decision maker, he is taking some decisions, and there is an adversary which fixes the input and the arrival order. And depending on the power of the adversary, you will define the power of the power of the algorithm or the competitive ratio. So there are 2 types of adversaries. One is called oblivious adversary, and the previous one, the competitive ratio definition that I mentioned, there it was actually oblivious adversary. So what happens in oblivious adversary is, so we are assuming in all these problems the adversary knows your algorithm. So it can be public. So adversary knows your algorithm, and based on your algorithm, it can actually produce an input. So it's kind of strong in that way. Now, in oblivious adversary, it knows the algorithm and it fixes the input sequence in advance. And it pays the optimal offline solution, the cost of the optimal offline solution. So it fixes the input sequence in advance, then your algorithm plays according to your algorithm, and you compare the solution of your algorithm with the optimal offline solution. That is what I defined in the previous definition as well. So here adversary does not have power. Once the decision maker starts his algorithm, it will just go along its algorithm. Now, sometimes what can happen is the decision maker might take a randomized algorithm. So the randomness is not available to the adversary. He can only see the algorithm, but it does not know in the algorithmic run what kind of randomness it will choose, and that can create difference. So in the other case, when you have adaptive adversary, the adversary is more powerful. It can choose action based on the previous actions taken by the algorithm. So think of the ski rental problem. So there the taxis are appearing one by one. So adversary can see, okay, I have assigned Chata Chaudhary in one of the taxis. Then it will choose a position of Dexter such that your algorithm performs bad. So based on your decision, the adversary chooses its action. And then there are two variants it can have. One is called adaptive online, other one is called adaptive offline. So in adaptive online, you serve your current request online. So you choose your particular particular input part, and you serve that input part online. And then you choose your next decision based on your algorithm's action so far, and you pay based on your action. So how whatever you are creating new input parts, you are taking a decision. The online algorithm also pays the adversary also pays the cost based on its decision that is taken. But in the adaptive offline case, you do the same. You choose the next request based on online algorithm's action so far. But instead of paying according to your actions, what you pay is assume you know all the input at the beginning of the input that you created, and then what was the optimal offline cost to serve that resulting sequence. And then you pay that amount. So it's much more powerful compared to the previous one. So oblivious adversary is called weak adversary. Adaptive online is called medium adversary. And adaptive offline is called strong adversary. So in this particular talk, we'll only focus on oblivious adversary, but it's just for you to know that there are multiple types of adversary which can be more powerful. So in this talk, we'll only focus on the case that the adversary knows the input sequence in advance, but it does not know the steps taken by the algorithm. Maybe it could be random, which it does not know, and you compare the solution of the algorithm with the optimal offline solution. Okay, so we'll only focus on the first oblivious adversary. That's this one. Any questions so far? So now we can start with one problem, and it's one of the canonical problems in online algorithms. It's called ski rental. So these kind of problems are also known as buy or rent. So think of, okay, in India, maybe it's not appropriate, but let's say you are in Europe or some US or Canada, some places where Winter Olympic happens, and there you want to go for skiing for some number of days. Now, skiing, you don't know how many days you will ski because the weather could be bad, there could be accidents and so on. So in online setting, you don't know how many days you'll go for skiing. Now you have two options. You can either buy the equipment, which is a one-time cost, B, or you can rent it each day for cost of, let's say, one per day. And your goal is to minimize the total cost over X days. So these kind of problems are called rent or buy problem. So think of in Indian context, you come to IISc for some internship, and maybe as a PhD student, and you don't know how many days you'll stay here. And you can, and it's a big campus, so you might want to either buy a bicycle or you want to rent a bicycle. So there are some services here where you can rent a bicycle for, let's say, 10 rupees per day, whereas you can buy a bicycle for maybe 5,000 rupees or something. So now you don't know how many days you'll bike. Maybe there will be rain, maybe there will be pandemic situations, you might have to go home, or other problems can happen. So you want to take a decision whether to buy a bicycle or you want to rent every day, the days you want to use. And your goal is to minimize the total cost over X days. So is the problem setting clear? If you have any question, let's say we buy with cost, one-time cost B, and rent is each day for a cost 1 per day. Now the thing is, if we know X, what is the best solution? Can anyone tell? Yes, so right answer. So if X is more than B, then we'll buy. Yeah, exactly. So, let's say B is equal to 1000 and you are paying 1 rupees per day for bicycle. And now if you do it for, if you buy for more than 1000 days, then you're already pay, if you rent every day, you are already paying more than 1000. So it's better to buy one time. So if you know X, it's quite simple. The problem is we don't know X. So then what can we do? So our goal is to minimize the cost, worst case cost. And I want to compare my algorithm's cost, the cost I pay, and the optimal solutions cost, even in the worst case. So yeah, that was the strategy that you mentioned, that buy at the beginning if X is more than B, otherwise you rent every day. Now let's study two strategy. So what is a competitive algorithm, a competitive ratio of an algorithm that buys on the first day? So if it buys on the first day, the cost it pays is B, right? And if it goes on skiing for X number of days, it pays X if it rents every day. So now you think of X equal to 1. So you only go for skiing once. Then the competitive ratio is B by 1, which is B. And that is quite bad. When B tends to infinity, a large value, then the ratio is 1000. Let's say B equal to 1000, then this ratio is 1000, which is quite kind of bad. So buying on the first day is a bad strategy, it seems. On the other hand, if you always rent, that's also a bad strategy because you may go for skiing n number of days, and then the competitive ratio is n by B, and it's also arbitrarily bad when n tends to infinity. So now I want to find an optimal strategy. Let's say I want to find some Y such that I rent for Y days and then I want to buy. So any guess what could be Y? Or what could be the competitive ratio there? Okay, maybe it will take some time to the calculation, but you can play, it's a homework, do the calculation. So what you can do is you rent for Y days and then you buy, and then you do some case analysis. What happens if X is less than Y, X is greater than Y, and maybe X is less than B, X is more than B, and this case analysis if you do, then actually you'll find the online strategy is something like this, that you rent for B minus 1 days, and then you buy in the next day. And this is the optimal deterministic strategy that you can have. And what is the competitive ratio of this algorithm? So in this case, you pay B minus, so you're renting for B minus 1 days. So if you only go skiing for less than B minus 1, less than equal to B minus 1 days, then you are very good because you're paying B minus this X number of amount, and also you're renting. So you're paying X amount of amount, optimal solution is also X, so it's 1. If it crosses B, then how much do you pay? In that case, the best optimal solution is to buy on the first day itself. So you pay only B, but your algorithm pays B minus 1 because it's renting for first B minus 1 days, and then you buy on the next day, you pay additional B. So you pay roughly a factor 2. So 2B minus 1 by B is factor 2. That is the competitive ratio of this break-even algorithm. Okay, it's a very simple strategy, and you can actually work it out. So just do this case analysis by hand and see this is the best strategy that you can have. If you follow this strategy that I rent for X number of days, Y number of days, and buy on the next day, then the optimal value of Y is actually B minus 1. And for that, we reach this competitive ratio of 2. Now it seems that this is the best you can do. You cannot do better than this, and one can formally prove this, that there is no deterministic online algorithm which can achieve a competitive ratio of less than 2. Now, in this problem, actually randomization helps. As I mentioned, there was this game being played by adversary and the decision maker. Now, if there is a randomization, then the adversary becomes less powerful because it knows the algorithm. but does not know the random bits that the algorithm will use. So it kind of bypasses some of the difficulties which adversary can pick up. For example, you may have one particular deterministic strategy, and for that, adversary can come up with one particular input arrival order and input instance for which your algorithm will perform bad. But then if you do randomization, maybe the algorithm will choose some other strategy with some probability. And then the adversary has to come up with another instance which is bad for both the strategies. And that could be problematic. Maybe the bad instance for one strategy is good for another strategy and vice versa. So randomization gives more power to the decision maker and makes the adversary weaker. In fact, one can find out the optimal online strategies as follows. So first, we define a probability PI. That is a probability that we rent for I days and buy on I plus 1th day. It's one of the strategies. There are many strategies, but one strategy is I rent for I days and then buy for I plus 1th day. And what we need is overall, after B days, let's say we always want to buy the equipment, but I want that in the first B minus 1 days, I should buy in one of the days I should buy the equipment. So that's what this condition says, that sum of P0s, P0, P1 up to PB minus 1 equal to 1. That means it's just saying that, okay, probability that we buy less than equal to B days, Bth day. We should buy the equipment before B days. That's what the condition is. And what turns out, you can choose this PI to be this kind of a number, which is C by B times 1 minus 1 by B to the power B minus 1 minus I, where C equal to this quantity. And that actually gives you a competitive ratio of E by E minus 1, which is 1.58. Now, I will not go into details of this proof because it normally uses linear programming, LP duality, and so on. But I'll mention a reference for this. Is a technique called primal dual techniques. And using primal dual techniques, you can come up with this kind of an algorithm. And one can show this is actually the best randomized algorithm. You cannot beat this E by E minus 1 factor for this algorithm. So randomization actually helps. And this algorithm right now, this number seems like a magic number. How are we coming up with this number? But it's a natural number which comes from primal dual analysis. I don't know if all of you have already come across linear program or not. So I will not go into primal dual analysis. But if you're interested, you can just search for ski rental primal dual analysis or go over the survey I'll mention by Bookbinder and Naur. There the proof is given how it works. But my point is just to say that randomization is very powerful. In some cases, deterministic algorithms, you cannot do much, but using randomization, you can do much better. In this particular example, you get, yes. So deterministic, the question is, using deterministic approach, the ratio was 2, and using randomization, the ratio is 1.58. That is correct. And both are tight. So using deterministic approach, you cannot do better than 2. And using randomization approach, you cannot get 1.58. So I will again mention the book name and everything at the end of the talk. It is by Bookbinder and Naur, a survey on primal dual techniques. I will go to the slide and mention all the books and all the resources about these problems. Also, if you're not able to find the resources, you can email me and I'll be happy to provide you the link of the resource again. Okay, so this is just saying that randomization is much more powerful. In online domain, it gives you much more power, and you can sometimes beat randomizations, the deterministic strategies using randomization. Okay, any question? Okay. So now let's go to the second problem called bin packing. So bin packing is one of the classical problems. It's actually the first problem for which approximation algorithm was studied. And this is a very known NP-hard problem. There are multiple techniques which came from bin packing problem. And this problem is this, that you are given n items, which have sizes between S1, S2, Sn, sizes S1, S2, Sn, and each number is a number between 0 and 1. And your goal is to pack all items into minimum number of unit bins. So think of an example that you are given some items 0.8, 0.6, 0.3, 0.2, and 0.1. And then you can pack them into 2 unit bins. Unit bins means the bin has size 1. So this is one bin, the second bin is this one. So they have size 1. So you can put 0.6, 0.1, and 0.3 in one bin. The sum is 0.6 plus 0.1 plus 0.3, which is less than equal to 1. And similarly, 0.8 and 0.2 is less than equal to 1. So your goal is, in a way, given this n items, you want to partition the items into minimum number of sets, which we call bin, such that if I take any set, the sum of the item sizes inside that set is at most 1. Okay. Is the problem definition fine? And this problem is NP hard. It comes from partition problem that given some items, you want to partition the items into 2 sets such that the sums are equal in both sets. That's called partition problem. It's NP hard, and one can reduce partition problem to bin packing problem, and the NP hardness of bin packing follows. And in fact, it turns out that you cannot distinguish in polynomial time if you need 2 bins or 3 bins, which gives a 3/2 strictly approximation ratio or absolute approximation ratio. But for this problem, actually much better things are known. You can actually attain, in polynomial time, you can attain opt plus order log opt approximation. So till now, I did not talk about the online version. It's just the offline version, which is already quite interesting and one of the key problems in approximation algorithms. So this is the offline bin packing problem. In the online setting, what happens is we are same. We have the n items with sizes between 0 to 1. But now the items are, you're not given the items at the beginning. They appear one by one. And we don't know the item sizes till they arrive. Once an item arrives, you get to see its size and you have to pack it. And you have to pack it immediately. And we cannot repack. Once you pack, that is the packing of the item. So we cannot move one packed item from one bin to other bin. And your goal is to pack all items using minimum number of bins. So what we can show actually, unlike the offline case where you can actually get almost 1 plus epsilon competitive ratio or approximation ratio, here you can actually cannot get better than 1.69 because of some information theoretic problem. So in online algorithms, you cannot achieve more than 1.69, even if you allow exponential time and maybe constant amount of space. You don't want to use too much amount of space. So let's see one such algorithm and the problem. So what could be the simplest algorithm? Simplest algorithm is once an item arrives, you just try to find a packing in the already packed bins and you pack it there. So this is called any fit kind of algorithm. And the most simple algorithm is called next fit, which is a greedy algorithm. So what happens is here you maintain only one open bin at a time. And if a new item arrives, and then in the open bin, if there is space available, you place the item there. And otherwise, if there is, you cannot place a new item in the bin, then you close the bin and you open a new bin and you continue. So take an example like this. So you have items of size 0.2, 0.9, 0.3, 0.8, and 0.4. And in the beginning, you're starting with one open bin. This is the bin. So is the problem definition fine? If you need time, I can go back to the previous slide and yeah, please feel free to stop me at any point of time, because if you don't understand the problem definition, then it will be difficult to follow the algorithm. Okay, so here the first item arrives, which is 0.2, this item, and then I want to place the item in the bin, and now I can place because it has size 1, so I have enough space. So I can place the item here. The 0.2 is packed. Now the second item arrives, which is 0.9. Now I cannot pack 0.9 in this bin because already 0.2 is packed. So if I pack 0.9, the size will be 0.2 plus 0.9, which is 1.1, which is more than 1. So I cannot pack 0.9 in this bin. So I close this bin and I open a new bin and I place 0.9 here. Then the third item comes and it is 0.3. Then I look at the present open bin and then try to pack 0.3, but I cannot do because then it again crosses 1, it becomes 1.2. So I have to open a new bin and place it here. And then the new item comes, which is 0.8, but again, I cannot pack it in this bin. So I open another new bin and pack it there. And then 0.4 comes, the last item. Again, I cannot pack it here because it crosses 1.2. It becomes 1.2. I pack it here. So it's the simplest strategy. I mean, it's the easiest thing that you can do. So this is called next fit algorithm, and it's very useful in practice because it's a simple algorithm. The running time is only order n. You don't have to do sorting or anything. Yes, that's a very good question. Devmal asked that, okay, why didn't we pack it in the previous bin? So we'll go to the next algorithm, which will do that. So the question is, let's say we are in this setting. So 0.2 came and then 0.3 came. Now in next fit, what happened is we only checked into this bin and we could not pack it. So we open a new bin and we pack it here. So Devmal asked, why can't we pack it here? Maybe there is already space available. Yes, we can do that. That's the next algorithm called first fit. So let me tell you why. Yes. So yeah, there are a lot of the Minalto, then the algorithm's runtime increases, which is correct. So there are multiple advantages of next fit. One is it's a very simple algorithm. Runtime is only order n. You don't have to really not runtime, but other complexity increases in the next algorithm. We'll see. So one thing is its runtime is very small, order n. Second thing is you don't have to keep in your memory. You don't have to keep a lot of things in mind. So only you're looking at a local one bin, and you look at that bin and you see if you can pack in that bin or not. So only you use only one open bin. So you use very less amount of memory. That's another thing. So that's the advantage of this next fit, that it's very fast. You use very small amount of memory. And what we'll show is not too bad either. The performance measure or competitive ratio is not too bad. So let's look at the analysis in the next slide. Yes, there are some other good candidate algorithms now. So Shamak says that we can sort and follow this. That's called next fit decreasing. So that's another algorithm which actually, given these items, you sort them and then you pack one by one, and that actually improves the factor. But before going to this complicated algorithm, let me just tell you the analysis for the simple algorithm. So many times what happens is you can give an algorithm, but it's difficult to analyze. So next fit advantage is it's very simple to analyze. Okay, so in this particular example, actually, next fit, as you see, it gave 5 bins, whereas the optimal solution was only using 3 bins. So it's kind of bad, the next fit. Its ratio is 5/3 in this case. But what is the worst case ratio we can have for next fit? So any guess for the competitive ratio for next fit? Okay, in the next analysis, we'll show it is actually factor 2. It's not too large. So as I mentioned, the advantage of next fit is only order n time, and it's constant amount of memory. It's very simple. Time and memory both are very limited amount of thing that you're using. Now let's look at this observation. Now I want to compare the optimal solution with your algorithm solution. Now already this problem is NP hard. So if computing optimal solution is already very difficult, it's not polynomial time solvable as of now. So what we'll do is, instead of comparing opt and your algorithm, you will compare with some lower bound on opt, which is easy to compute. So we know that opt is at least the sum of the sizes of all items. Why? Because if we look at the optimal solution here, each bin has size 1. So if you look at the sum of the sizes of items packed in a bin, it is less than equal to 1. So if I look at sum of all items, or the item sizes, that's at most less than equal to the size, the number of bins opt. So this one, sum of sizes of all items, it is providing you a lower bound on opt. So for example, in this case, 0.2 plus 0.9 is 1.1, 1.4, 2.2, 2.6. The sum of the item sizes is 2.6, and opt is 3. So opt is actually greater than equal to the sum of item sizes. So that's a good lower bound on opt. Now, second observation we have is, in the final packing, total size of items in each 2 consecutive bins is larger than 1. And that is also kind of obvious from the strategy of next fit. So what happens is if we have one open bin and then one item comes, we are only opening a new bin if the new item cannot be packed in the previous bin. So that size of the old bin plus the new item that arrives, the sum is crossing 1. So that means and the next item was placed in the next bin. So if I look at the first bin and the second bin, the sum of the item sizes will be at least 1. If you think of the example, the item size was 0.2 here, the bin size, and the items packed in this bin was 0.2, this was 0.9, 0.3, 0.8, and 0.4. If I sum this to, it's 1.1, 1.2, 1.1, and then 1.2, and so on. So in all these cases, if I take 2 consecutive bins, their total size is more than equal to 1. Okay. Any question? Now we want to use these 2 observations together and we'll give an analysis. So first observation is we look at NF by 2. NF is the number of bins used by next fit, which is same as I'm just using a sum and I'm just breaking into I plus 1 to NF by 2. There are NF by 2 ones. So 1 plus 1 plus 1, NF by 2 t times, NF by 2 times. And instead of 1, now I am using this quantity from this observation, that the size of items in any 2 consecutive bin is more than 1. So I partition the bins into 2 sets of 2 bins, and each of them has size 1. So I have NF by 2 such partitions, and each of them has size at least 1. So this is giving you size of items in 2a minus 1th bin plus size of items in 2ith bin, and this is greater than or equal to 1. So I use this strict inequality from this observation. And this is actually, this term is actually sum of all item sizes, right? Because this is all the bins that we have and all items are packed in bin packing. So it's just sum of all item sizes. And already we know that opt is a lower bound on this quantity, sum of item sizes, because of this first property. So this one is giving you that opt is greater than NF by 2. And now we know that opt is less than or equal to NF because it's a minimization problem, it's an optimal solution. So this one was already known. And the other one is this one. And this is showing that next fit is 2 approximation algorithm or 2 competitive algorithm. So it's a very simple way to analyze the algorithm and you get a 2 approximation for this problem. Any question? So can we do better? Now there are multiple ways. The first one will be first fit, which will use slightly more time per step. Now instead of previously actually per step it was only constant amount of time. Now it's more order n amount of time and total order n square amount of time. And also it uses order n memory. So what it happens is you consider all bins and place an item in the first bin where there is space. Otherwise, you open a new bin and place it there. So one can show that first fit packs items in 1.7 opt number of bins. But now the analysis is very complicated. It's not that simple as the previous one. It is based on weight functions. And I will also give you reference for this one at the end. So what is the algorithm? Let's go over once more. So we had this item 0.2, 0.9, 0.3, 0.8, and 0.4. Now the first bin is there and 0.2 is packed there. And then 0.9 comes and you cannot pack in the open bin. So you open the new bin and pack 0.9 there. Then 0.3 comes. Now unlike next fit where we only look at this bin and we could not pack 0.3 here, now we can actually look at all the previously open bins. And in this particular case, among all the previous bins, the first bin is actually good for the item, like 0.3, I can pack it here. So I pack it there. So among all the available bins, you pack it in the first bin where it fits. And then the next item comes, which is 0.8, and you cannot fit it in the previous 2 open bins. You open a new bin and place it here. And the last item comes 0.4, and you pack in the first open bin. The difference with the previous algorithm is now you keep all the bins open, but once an item comes, instead of just looking into one bin, which was a constant time affair, now you have to look into all the previous open bins and see which one is open for the first bin where it fits. So in the worst case, it can take order n or n square in total time for n steps. So it uses more time and more memory, but you can also get the performance ratio better, 1.7. And there are other variants where I think someone pointed out the sorting variant, where one can actually sort the item and pack it. But in the online setting, we cannot do that, because for sorting, we need to know all the items in the beginning. So if you sort, if you want to sort the items, then you can do it in the offline case when you know all the items. But in the online case, you cannot do. So it turns out first fit is one of the almost optimal algorithm for online case. In the offline case, you can do much better using this sorting or other arguments. And as I mentioned, you can actually get opt plus order log opt approximation algorithm, which is better than 1 plus epsilon approximation in the offline case, with using more complicated techniques like discrepancy based rounding, etc. But for the online case, this is kind of the best first fit. There is one algorithm which beats first fit. I will talk about that. And that turns out to be the best algorithm in general for bin packing under some assumptions. But any question about first fit? At least why, what is the advantage of first fit and next fit? One is more simple, takes less time and memory. Other one is slightly complicated, takes more time and memory, but gives you better performance ratio. Okay. The next algorithm is called harmonic algorithm. It's by Lee and Lee, which appeared in this journal JACM in '85, which is slightly more complicated. So what happens is you classify items into some classes, and we call it harmonic class. So if the item size is between 1 by k plus 1 and 1 by k, we call it class k. So take an example. So think of if the items are half plus epsilon. Say epsilon is a small number, let's say 0.001 or something. So then this item size is in half and 1. So according to this definition, it's in class 1. If the items are 1/3 plus epsilon, then that is in class 2, because item sizes are between 1/3 and half. If it is 1/6 minus 2 epsilon, then the item size is between 1/7 and 1/6. So the class is 6. So you classify. So you classify the item based on the sizes to some k classes and some m classes, where m is let's say 10,000 or some number, large number. And if the item is smaller than 1 by m, we call it class m. So what happens? The algorithm is this: that we keep m number of open bins, 1 for each of the class. And once an item of class k comes, we look at the corresponding open bin. If there is a space, we put the item in that bin. And if it is not available, then we open a new bin and continue. Okay. And it turns out this gives you a 1.69103 competitive algorithm. And this is actually the best you can do if all we are allowed is to keep only constant number of bins open. So we keep open m number of bins, m is a constant, then it is the best you can do. So in first fit, actually, we are opening more number of bins. And if you open more bins, you can actually improve this 1.69 factor. But like next fit, where we only had one open bin, if you allow only constant number of open bins, which is practically relevant because you don't want to keep all the bins open because the runtime becomes more, then this is the best you can do. So think of this example, and maybe you can work offline and think how this algorithm performs for this algorithm at this particular instance. For example, what happens in this case? How many bins are required? So you have n by 3 items of size half plus epsilon. So in your algorithm, you keep these are belonging to class 1, and in class 1, you pack all the items in class 1. In this, you open a bin and you look at the class 1 item and put it there. If you cannot put, you open a new bin. So how many bins you require for this n by 3 items? You need actually n by 3 bins, because half plus epsilon items can only be packed one item in a bin. You cannot pack two items in a bin. Similarly, you cannot pack more than 2 items of size 1/3 plus epsilon in a bin. If you pack 3, it crosses 1. So for n by 3 items of size 1/3 plus epsilon, you will need n by 3 by 2 number of bins. And similarly for the other case, when you have 1/6 minus 2 epsilon, you can at most pack 6 items in a bin. You cannot pack more than 6 items in a bin. So it's n by 3 by 6 number of bins that you require. So if you do the sum, it becomes n by 3, 1 plus half plus 1/6, which is like 6 plus 3 plus 1, so 10 by 6, which is like 5 by 3. So it's like 1.67 factor that you lose in the algorithm. It's a bad example. You lose 1.67 factor. And the optimal solution in this case was actually only n by 3 bins. So you can pack half plus epsilon, 1/3 plus epsilon, and 1/6 minus 2 epsilon, 3 items in a bin, and that will give you only n by 3 bins. So instead of n by 3, you are now having n by 3 times 1.67 number of bins by this algorithm. But it turns out it is not very far from the worst case. Even in the worst case, you can get 1.69 competitive algorithm, which is the best you can do if you keep constant number of bins open. So again, this is the paper. If you search in Google Scholar, you will find this Lee and Lee paper on harmonic algorithm. But the point is, as you see, in this online algorithmic questions, depending on how much power you give to the algorithm, the runtime, amount of memory that you have, the algorithm's power can be different. But then there is some limitations. I mean, even if you give unlimited amount of time, you cannot really beat 1.69103 competitive algorithm if you keep this restriction that only constant number of bins are open. Any question? So now we go to the next important problem, and probably the most important online algorithm, called online matching. So think of when you Google search something, then actually you see some Google ads, and then you see some other results. So what happens is actually there are some advertisers who want to show their advertisement to the user. So when a user searches something, then based on user's profile, you see what are the relevant ads for the user, and you want to show those ads to the user. So there are users and advertisers, and they are forming some kind of bipartite graph. And if some user appears, then you look at what are the possible advertisers which he might be interested in based on his profile. So it creates some kind of edges. So he may not be interested in all the advertisers, but some subset of advertisers, and you create an edge between the advertiser and the buyer or user if he is interested in the product. And for now, assume that each user can see only one ad, and each ad can be shown to one user, because these companies are paying some amount of money. So for one ad slot, they're paying some amount of money. So you don't want to sell the same ad slot to, you don't want to show multiple ads corresponding to one particular ad slot. So you want to only show one ad to one user. And your goal is to maximize matches. You want to match as many buyers and advertisers as possible, because on one hand, you want to satisfy the buyers because you want to match many of them. Also, you want to satisfy the advertisers such that kind of you only show relevant ads to the advertisers. You don't show not relevant ads, irrelevant ads. Okay. So it turns out it's basically a bipartite matching question. Yes, this is a variant of assignment problem. Samaksh asked the question. This is a variant of assignment problem. So actually, the most simple case I will talk about is basically a matching problem, but assignment problem or generalized assignment problem is a much more generalized problem. And there are many variants of this problem which are studied. In fact, the reason I said it's probably the most important online algorithm is because of its importance in ad allocation. And in Google or Microsoft, in many places, the main source of revenue is basically this ad allocation. So this is $1 billion problem, maybe $1 trillion problem in some way. So let's explain this using a picture. So what happens is you have some advertisers, let's say Coca-Cola, Pepsi, and Sprite, and then users appear one by one. Maybe first it's Captain Haddock. Captain Haddock appears, and he likes drinks, so he likes all kinds of drinks: Coca-Cola, Pepsi, and Sprite. So why should one ad be shown to only one user? Yeah, so that's an assumption I'm assuming, because this, I'm not saying only the one ad should be shown to one user, but let's say one ad slot. So each of these companies, they have paid some amount of money for, let's say, some amount of slots. So 1,000 slots for an ad. So you don't want to show the ads, 1,000 ads to 1,001 people, because that's kind of unfair to other advertisers. So you only want to show, if they have paid for 1,000 ads, then you will show only 1,000 users. So it's not one ad, but basically one ad slot should be shown to only one user. Okay. Yeah, so in this case, then he arrives with this Captain Haddock arrives, and there are 3 drinks he's interested in, and then probably you show the ad of Coca-Cola to him. Then probably next is about calculus, and he's interested only in maybe Coca-Cola and Sprite. And then you probably assign him to Sprite. And then probably Bianca Castafiore comes, and she's only interested in Coca-Cola and Sprite. But now you have already shown Coca-Cola and Sprite to other people, so you cannot show this ad to this person. The slot is finished, and Pepsi is left, but I cannot show Pepsi because she is not interested in Pepsi. Okay. So that's the problem. But it is basically a bipartite matching question. That it's a bipartite graph. Left side is users or buyers, and right side it's sorry, left side is advertisers or sellers, and right side is buyers. The buyers arrive one by one, and you get to see the interesting edges for them. And then you want to maximize the amount of matches, or you want to find the maximum matching. So is the context clear why it's a maximum matching problem in a bipartite graph? So now you see in this algorithm, there are 2 things which are playing a role. One is the underlying input graph, the offline graph, and second one is arrival order of vertices. So the algorithm on same offline graph can have different solutions depending on the arrival order of vertices. So in this example, the offline solution, best solution was probably assign Haddock to Pepsi, calculus to Coca-Cola, and Bianca to Sprite. But as they appeared in this order, we could not really do it in our algorithm. But maybe in some other order, if they arrived, maybe we could have solved the problem. So maybe first, if Bianca arrives, then we could have assigned to Sprite. And then if calculus arrived, we could have assigned to maybe Coca-Cola. And then if Haddock arrived, we could assign him to maybe second one, Pepsi. So arrival order plays a role, and input graph. There are 2 things which are playing a key component in the problem. Now, what is the simplest algorithm? Simplest algorithm is again the greedy algorithm. So once some person arrives, you just choose one of its available neighbors and just assign that. So maybe Haddock arrives and you just assign Coca-Cola to him and you're done. And then the problem is then you can show this is actually a good algorithm. It's not too bad. It achieves 2 approximation. And the reason that it achieves 2 approximation is because in the greedy algorithm, we are trying to find a offline maximal matching. So if a item arrives, if there is an available edge, I put an edge. Otherwise, if I'm not able to put an edge, that means the other vertex is already matched. That's why I cannot put an edge between them. So it will return a maximal matching. And there is a property from graph theory which can show the size of maximum matching in the graph is at most 2 times size of maximal matching. Okay. So I don't know if you know about these 2 definitions, maximal and maximum. So maximum matching is just the optimal matching in the offline graph. And maximal matching it's a greedy algorithm. You start with one edge and then you try to add another edge if you can add. And you can add only the other edge if none of the endpoints share with any of the other edges. It's a greedy way of adding edges, and then that gives you a maximal matching. And one can show maximal and maximum matchings are not too far. It's within a factor 2. So let me give you an example. So maybe in this example, in this graph, this red edge is already a maximal matching because I cannot add any more edges. And this red edge itself it's a maximum matching. Whereas the blue edges is a maximum matching. So I can add both this and this, it's a matching edge, two matching edges, and that's the maximum matching. So in this particular example, maximal matching is 1 for this particular case, and the maximum matching is 2. Maximum matching is also maximal matching. So maximal matching can have values between half of the maximum matching and maximum matching. Okay. So this proof idea is this, that size of maximum matching is at most 2 times size of maximal matching. And that shows the algorithm is 2 approximation. And it turns out there is no deterministic algorithm which can achieve a less than 2 competitive ratio. So in this particular problem, actually the hardness comes from the fact that you don't know the future input. Otherwise, matching is an easy problem. You can solve bipartite matching in polynomial time. But though you can solve the offline problem optimally, the online problem is harder. You cannot get better than factor 2 competitive ratio, even if you give unlimited amount of time, because of the information theory problem, that you don't know all the items. So for example, if you take this example, so in this example, let's say I have Coca-Cola here and then Pepsi here, so C and P, and then haddock here, and maybe calculus I'll write K instead of C. So now let's say the first guy arrives, haddock, and maybe he has 2 edges like this. Now you have 2 strategies. Either you will choose this edge or you choose this edge. Now in the first case, if you choose, maybe the second one arrives. So you already picked this edge. The second one arrives like this, haddock, calculus. He's only interested in this edge. So in this case, you only assigned 1 edge and you cannot do better than this. And the second case, if you assigned this edge like this, then maybe calculus appears and he's only interested in this edge. Then again, you cannot add this edge. So whatever time you took, the difficulty is coming from the fact that you don't know the future input, what is coming next. So if you choose the first edge, you do poor in this graph. If you choose second edge, you do poor in the second graph. You cannot beat factor 2. The optimal solution was 2 and your algorithm only gave 1. So deterministic algorithm cannot beat factor 2. So Prashant asked the question that what is the maximum is global the best? Yes. So maximum matching is the global best matching that we can have. The offline matching that we can have. And maximal matching is just a greedy algorithm. It's a set of edges such that if I add any more edge from the graph to this set of edges, then it will have one endpoint in one of these edges. So I cannot increase the matching further by adding any more edges from the graph. So edges correspond to user is maximum cost or random. So here there is no cost. I should have mentioned this is just an unweighted matching version. So there are weighted version as well, but in this particular case, I'm just using unweighted graph. So all edge costs are 1. So deterministic algorithm cannot beat factor 2. So you might think maybe randomization will help. So one simple strategy is once an user arrives, maybe this guy, then he has 2 possible choices, possible choice A and possible choice B. There are 2 edges, and I just randomly choose one of these 2 edges. And that is already good, because what happens, let's say I choose with half probability edge A and half probability edge B, then at least that will do good in this example, the below example that I provided, because with half probability I will choose this edge 1, and with half I'll choose edge 2. So adversary fixes the input. We are assuming that adversary is fixing the input in the beginning. So maybe he fixes this input. So then with half probability, we'll have 1 in the algorithm. And with half probability, we'll have factor 2. If I already chose this edge, then when calculus comes, I can add this edge and I'll get 2 in the algorithm. So I get actually half plus 1, 3 by 2. So now the ratio becomes 2 versus 3 by 2, which is 4 by 3, better than factor 2. So you can beat factor 2 for this example. But it turns out this is not always the case. There are examples where even if you do this strategy, it will fail. So let me draw such an example here. So maybe you will have some edges like this. And this part, there's a complete graph. So all the edges have edges between this. So if you have this kind of a graph, what happens is if a vertex arrives here, then most of its neighbors are here in this set B, maybe it's equal A, B, C, D. And A has only one neighbor. So if you randomly choose a neighbor, then you will pick a neighbor in B. So for all these nodes in C, once they appear, you will mostly pick neighbor from B. So B will be kind of exhausted. So once D appears, you will not be able to match D because all these edges in most of the vertices that are in B are already matched. So one can show formally with this example that you can achieve almost factor 2 hardness for this problem, for this graph. So this randomized strategy does not work out. So here randomization helps, but in another different algorithm, which is called ranking. So this algorithm appeared in 1990, and it was by Karp Vazirani and Vazirani. And at that time, there was no Google or no Microsoft, or I mean, Microsoft was there, but no ad allocation kind of problems were not that relevant in internet. So they just studied from a theoretical point of view. It's just a bipartite matching problem, which is a classical theory problem. So they studied it from that point of view. And after 15, 20 years, it turns out this became the trillion-dollar problem. So sometimes it happens in theory that when you work on a problem, it may not have application immediately, but after a few years or decades or sometimes 1,000 years, like in number theory, it will find applications. So the algorithm is follows. You pick a random permutation of the left side of vertices, and that induces a ranking. So you have this Coca-Cola, Pepsi, and Sprite. You take a random permutation. So maybe you in this permutation is 1, 2, 3, but maybe you can take 3, 2, 1. So there are n factorial possible permutations. You take one of the possible permutations of the left side. And when a new vertex arrives, you match it to the highest ranked neighbor. So when this guy arrives, Haddock, then you match it to rank 1. So there are 3 vertex on the left in which he is interested in. You match it to the highest ranked neighbor, rank 1, and the next person arrives, he's interested in 2, but you match it to the highest ranked neighbor, and then third one arrives, you match it to the highest ranked neighbor. Highest ranked available neighbor. So for example, here when Bianca Castafiore arrives, she's interested in 2, but this one was already taken, so I cannot do this. So among the remaining one, the highest ranked neighbor is this one, so I assign it here. And it turns out this actually beats factor 2, and this gives you again E by E minus 1 ratio, which is 1.58, and one can show this is the best one can do. Yeah, rank is like a priority. So the point is, we want to, once a user arrives, you get to see its edges, and we want to kind of assign one of the edges to the user, and there should be some kind of a property or function. So one was just a greedy algorithm where I could choose any edges, which failed miserably. It's factor 2. The other one was I can choose just randomly one of the edges, which again will fail. It will not be factor 2. The third one is kind of a, so the previous the algorithm that we mentioned, this randomly choosing one of the edges, in that case, it's kind of independently doing for all the vertices. There is no correlation. So ranking helps because if there is some kind of correlation among the vertices, you have a ranking that induces some kind of an order between the vertices, and you just follow that order. So whenever a vertex arrives, you look at the highest ranked neighbor and you assign to that and continue. And it turns out this actually breaks this barrier of 2. And it is a very powerful algorithm. So in general, I mentioned the very basic case, which is the unweighted matching with one-sided arrival. So one side is given offline, other side is arriving one by one. It's called node arrival. Nodes arrive one by one. So there are many variants of this problem. You can have a general graph, not bipartite graph, or you can have edge arrival, or you can have weighted graph, or you can have, instead of one edge, you can have B matching. You can maybe have a couple of B edges. You can show for each assign for each vertex, or you can have generalized assignment problem, which is even more general problem. So all these problems, it turns out ranking or a variant of ranking has been very successful on all these problems. And there are multiple surveys. I'll mention one of the survey at the end of the talk about this problem. And it's still an active area of research. And in many cases, actually, we know ranking performs very good in practice, but we don't really understand the tightness. So the research is kind of is involved in showing the tight hardness or tight analysis of the algorithm ranking for the special cases of the problems. Any question? Now, as we looked at the problem, we saw that unlike an offline problem where the worst case is defined by the worst case input, here there is also an arrival order, which is important. The adversarial order arrival can be quite bad, but sometimes it can be too pessimistic. So if the adversary chooses both the input and the arrival order, sometimes you cannot do much. You cannot even get any bounded competitive ratio, even not n cube or something. But sometimes you cannot get any bounded factor. So for those problems, what we do is we consider something called random order arrival. So the adversary fixes the input, but the arrival order is random. So you can think of the user has the flexibility to choose items from the part of the input. So it will randomly permute the input and then call one by one. So that gives more power to the user or decision maker. And we'll see some example of such problems. So the problem which is prototypical in this problem, in this area, is called secretary problem. So in this problem, okay, let me define or explain the problem in terms of a marriage problem. It's also called marriage problem. So Jasmine wants to get married, and there are n candidates for her, and the candidates arrive one by one. So first maybe Deadpool arrived with value 5, and then maybe Mickey with 7, then Aladdin with 10, and Shrek with 6. Now the thing is, she does not know who will come. So it's kind of online nature. So she will date one by one. So once the candidate arrives, she gets to see its score, and based on that, she will either decide to marry the person, and then the future candidates will not appear, or she will reject the person, and then she will not marry this person, and the next person appears. So it's kind of Swayamvar process in Indian mythology, where the princess can choose the person, and once she rejects someone, the person goes away, and the next person appears. Okay. So once a candidate arrives, then only we see its value, and decision maker can either select or reject. And if she selects, she marries the selected candidate. If she rejects, then she gets to see more candidates, but the decision is irrevocable. Now it turns out, and the goal is to find the best match. So in this particular case, she wants to get married to Aladdin because he has the highest value 10. Now, if you have adversarial order arrival, then it's kind of hopeless because adversary can choose very bad order, and Jasmine may not have enough information, so you cannot actually do anything if it's adversarial order arrival. So what we'll see is random order arrival. So what the process is, now among the candidates, she will just randomly permute the candidates and then call them one by one. And it seems then it's much more powerful and you can do better. So this problem is quite common in many places. Think of you are interviewing secretary, or you have multiple jobs. You don't know which job is good or bad unless you go to the job and you work for one day. You will realize, okay, this is this much amount of value, and based on that you can either continue in the job or you can reject and go to the next job and so on. There are multiple scenarios where this problem has been studied. Now in the random order arrival, what we do is we again have these n candidates. You took a random permutation pi of these n candidates. There are n candidates, so there are n factorial possible permutations, and you take a random permutation, and then the suitors arrive one by one sequentially according to pi, and then you find the maximum. You want to find the best candidate in expectation. So maximize the expected value of the accepted candidate. That's your goal. So so what could we do? So it's a random order arrival. So one option you can see is maybe in general you'll probably sample the first few guys. So first few guys you will just look at them to get an estimate of the whole population. You'll believe it's a random permutation. So if I see first few guys, I will get an idea about the whole population. So sampling kind of an idea. Now the problem is if you have very large sample, that's good because then you have much more information about the candidate pool. But the problem could be that maybe in the sampled thing you're not selecting any candidate because you want to get information about this sample. So, and it could be the case the best candidate here is already in the sample. So then you lose that person. So having large sample size is good for getting information, but bad for selecting the best candidate. On the other hand, if you have very small sample size, then what can happen is you may not have relevant information, and maybe you will select some non-optimal person and not the best person. So you want a sweet spot where the sample size is not too big, not too small. So sample means that the items are coming one by one. I want to see maybe first few users or first few candidates, and then based on, so once a candidate comes, I see their value. So I use this first few candidates as sample of the whole population, and based on the first few candidates I see, I kind of try to, I kind of expect this small set of candidates to be a sample or some kind of a representative set of the whole population, and I want to estimate the property of the whole population based on the first few candidates. So you want to select, you want to see some number of candidates, which I call sample, and then based on this properties of the first few candidates, I want to take a decision to, for the algorithm for the next candidate pool, such that I do kind of perform kind of good. Okay. So the algorithm is as follows. In fact, it turns out to be the optimal strategy when n is large. Then you reject the first n by e candidates. So the candidates are arriving randomly one by one. Say n by e is like 37% or 36% of the candidates. They come, you observe their values, but you don't accept them. So in this case, maybe Deadpool comes and maybe Mickey comes, and then you reject both of them. And you see their values 5 and 7. And you remember the best candidate in this set S, which is in this case Mickey, value 7. And then what happens is next candidates appear one by one after n by e, and whenever a candidate comes which has value at least greater than or equal to p, you select the person. And it turns out this gives you a 1 by e competitive ratio, and this is the best you can do in this case. So the first 37% you don't do anything, you just look at them and see the best candidate in this 37%, and then you look at the next candidate, which is the best candidate among, which is better than the previous best candidates in S, and you select it. Okay. I have 4 minutes left, so I have to skip the analysis, I guess. So it turns out, I'll share the slides, but it turns out what happens is you can show with probability 1 by e, you can select the best candidate. And that comes from the fact that, okay, if P is the best candidate in the set sample set S, and C star is the best candidate optimally, then I want to select C star, and it is selected only if it comes in some ith round, and we accept in ith round, and we sum over all possible ith round. And then the probability that C comes in ith round is 1 by n, because it's a random permutation. So any of this 1 by n with probability 1 by n. Yeah, if Aladdin comes, why don't we first select him? Because I don't know the value. So maybe 10 is the best in this case, but maybe there is, after that there is 1000. Someone comes with value 1000. So I don't know what is the best candidate. So even if Aladdin comes, I only see 10. I don't know if future candidates will be better than 10 or not. And then what is the probability we accept in ith round? It means that whatever I look at the first I minus 1 element, and the best among this I minus 1 should appear in the first n by e. It should not appear here, because then we'll select that item. And it turns out that probability is this probability, and with some calculation you can show 1 by e. It's kind of simple. I don't have much time, so I'll not go over the calculation, but you just read it and you'll understand. The techniques that we have here, it has interplay of different areas. So in approximation algorithm, maybe you have already come across this dynamic program, local search, linear program, rounding of data, spectral methods, and so on. Now, in online algorithms, many techniques from approximation algorithms are also useful, like greedy algorithms, as we saw for next fit. There is dual fitting and primal dual methods, which I mentioned for in the context of ski rental. Also, the ranking algorithm that I mentioned, that also the analysis can be formed as a primal dual method kind of algorithm, which is based on linear program. So it's a common technique between approximation and online algorithms. And then online algorithms has its own techniques like doubling, potential methods, work function, Fenchel duality, and so on. And it has link with online learning, which is a sub area of machine learning, where you want to learn some kind of function or some property. And there are techniques like regularization, which is useful in both online algorithms and online learning. There is also online convex optimization, where you have a convex optimization problem you want to solve online. And there are techniques like mirror descent are there, or gradient descent. They're also useful in online algorithms. So in general, the analysis has a lot of techniques from math, like probability, linear algebra, calculus, abstract algebra, convex optimization, graph theory. And using these math tools, we analyze the algorithms and give a provable guarantee. And this is some related interesting problems: load balancing, scheduling, network routing, graph coloring, paging, K-server. So K-server is another kind of key open problem or key problem studied in online algorithms. Online learning, online traveling salesman problem, online staynet tree, online facility location, online set cover. So all these combinatorial problems that you study for approximation or parameterize, many of them are important for online setting. And the books actually cover these things in detail. And there are many related methods: online learning, online convex optimization, dynamic algorithms, where this online setting items can arrive as well as depart. And there is streaming algorithms, where it's an online algorithm, but you have limited amount of memory, and then you want to solve the problem. There is recourse. So in the problems I defined previously, I cannot change the decision. It's irrevocable. But sometimes you're allowed to change your decision sometimes. It's called recourse. Maybe you can change constant times your decision you can change over the algorithm. There's random order arrival, which I mentioned. There's also IID model, where you can assume that items arrive from some distribution. And there is also with advice, where the algorithm can get some more advice about the input or about the problem from some oracle, and based on that you can solve the problem. So these are the references. So the two books I mentioned, one is Borodin Eliani, the other one is by Fiat et al. And then there are surveys. One is by Susan Albers, another one is by Bookbinder now. So this is the survey which covers the ski rental algorithm that I mentioned. And also it talks about matching ranking a bit. And if you Google search about Bookbinder primal dual survey, you'll find some videos as well. So you'll some lectures on this topic as well. There are multiple workshops in this topic. One is called Algorithms and Uncertainty by Simons Institute for Theory of Computing. So if you Google search again this, then you will get the web page. And in the web page, there are a lot of video talks. And one of them is actually this video, which is this primal dual survey by Bookbinder. I think Bookbinder or Naur, one of them gave the survey. Naur, Sefi Naur gave the survey. And then we have online algorithms and learning workshop. If you Google search, you'll find this kind of workshops where there are many interesting papers or problems that are mentioned. And then there are more references. So there are some courses taught by Anupam Gupta in CMU, or Nikhil Bansal in Berkeley, Bubek and Lee in University of Washington, Kamesh Munagala at Duke, Yossi Azar at Tel Aviv University, and Shaheen Kamali at Manitoba, where they've covered online algorithms or some variants. So these are good resources to learn about this area in detail. There are some surveys. The first one is online matching and ad allocation. If you want to learn about this ranking algorithm, their analysis and so on, this is a very good survey. If you want to know about bin packing or this variant of bin packing or knapsack, so we have a survey by Christiansen et al. From 2017. It's also there in my web page on this topic. This online scheduling survey by Susan Albers. There are surveys on hardness. How do you prove the hardness or the best? What is the best thing that you can do with online algorithms? There is a survey on that topic, and there is also online algorithms with advice, a survey on this topic. So these references I will provide on my web page. And if you don't find any of these references, just send me an email, and I'll be happy to provide more resources on this.
So there is one question on chat.
Yes. So does streaming and online differ in storage space? So there are some other differences too. So actually in streaming, there are multiple types of algorithms. So there is something called passes. So in streaming, you have an input, and the input arrives one by one. Now in single pass, it's only one pass. So they arrive one by one, and then they depart. You cannot have access to them again. So single pass and online are very similar. And the difference is only in the storage space. But there is other algorithm in streaming which is called multiple pass, where actually you can pass the input multiple times. So there it's no more online. So you can actually read it many times. The constraint comes more from the memory. You can only keep a small amount of things in the memory. So yeah, so in the single page streaming and online, they differ only in the storage space, but multiple pass, it's different. Any other questions?
Oh, do we have a online algorithm with deadlines? Kind of, I mean, you can wait for some time before we modify the output, like for example, matching.
So there is something called buffer, or
Okay.
so buffer is something like you have, let's say the matching, your nodes are arriving, and you maybe you don't want to take a decision when one node arrives. You can wait for 10 nodes to arrive, and then you can take a decision. It's called buffer.
Okay.
You can
Okay.
keep things in buffer and then take a decision.
So as the complexity, generally the complexity is, does it improve when it?
In some problems it's improved, but in some problems it's still the same.
Okay,
I mean,
it
as long
depends
as,
on the problem.
yeah, I mean, okay, if you have this buffer to be like all the input, like complete input, then also the offline and online are equal. Then you cannot do. I mean, it's the same. But if you have small buffer size, it's a constant, then normally it does not help a lot. Sometimes it helps a bit, but it does not help a lot. So there is another question: if we need multiple paths, then all data needs to be stored. No, I mean, what happens in multiple paths is your storage space is limited. You only have small amount of storage space, but you can read the data multiple times. So storage space is still the same, but maybe when you read something and I mean, maybe think of secondary problem. If I tell you you are only allowed to read once, then you cannot do better in the adversarial case because you don't know what is the next item. So you just, I mean, you have to select an item and keep it in the solution. That you cannot do. But if I allow two paths, then what you will do is you read all the items and remember which one is the best item at the end. And at the next pass, if you only select when that item comes. So in one pass you cannot do much, but in two pass you can do better. But you only store one item, the value of the optimal item.
Okay,
So-
we are concluding this session. Thank you, Professor Arindam, for an informative session and for finding time to take the questions. Thank you, Professor.